I am Mike, and we are the Toronto C++ user group. Woo woo. It was nice enough outside. We decided to do the first part of the networking outside tonight. I hope you liked it. The land on which we're meeting has been the site of human activity for over 15,000 years. We recognize the enduring presence of indigenous people connected to and on this land. We're grateful for the opportunity to gather here and to work in this community, and we commit ourselves to the work of reconciliation with the indigenous peoples. I'd like to thank our sponsors. The hosting sponsor tonight is Autodesk, represented tonight through thick and thin by KC Concepcion, who I don't see, but thank you, KC. Meeting C++ has also provided publicity for the event. Also like to thank my co-organizer, Jason Walter, in the back, my wife, Lanny Milstein. I'd like to thank Include C++, is a global, inclusive, and diverse community for developers interested in C++. Please go sign up on their Discord. It's like a chat server if you haven't used Discord. Very knowledgeable people, everybody nice, everybody will want to help you. You'll go just to talk to them. Best place to learn about C++, to talk about C++. Okay, finally I would also like to thank Kate Gregory, who is basically the spirit guide for this group. And Kate actually would like to say a few words to the group.
I like the outside mingling. I think we should do that on purpose, actually, in future, especially as it gets warmer. What I wanted to talk about was being a speaker. Give me your hands if you've already spoken in public or at work. Okay. Now, who has just one little tiny corner somewhere in their heart that thinks it would be cool to be a person who could speak in public? Tell the truth. Okay. So I want to encourage you to listen to that corner and to do that. Okay? I won't say that it isn't hard, because it is hard, but it isn't as hard as you think it is. Okay? And most importantly, public speaking is a learned skill. It is not true that some people are magically good at it and everyone else sucks at it and should stay away. You can learn how to do it, and how to do it very well indeed. One of the places you could learn how to do it is the Discord server that Mike mentioned. We have a channel called Speaking. It's for our established members. Some of our channels are protected, and you can't just get into them on the first day. And some of our other homes had a bit of a troll problem. So join, talk about C++, talk about game development, talk about IDEs and editors, all the things that happen in our public channels. And then once you're an established member, you can join the Speaking channel. We have been writing people's bios. This last month, we have been writing people's abstracts. We have been gathering around and helping people to do their first ever talk. The best place in the world to do a first talk is at a user group, because it's relatively small, you're on your home turf, you're not dealing with jet lag, you're going to sleep in your own bed afterwards, and it's kind of your home team. We all want to see anyone do well. So if you want to come up here and tell us about a cool thing you did at work, we are going to be there cheering you on and wanting you to be great, and you probably will be. Anyone who wants any kind of speaking, mentoring help, DM me on Twitter or the Discord, or send me an email. My email address is not hard to find. I've had the same email address since 1988 or so, and it's like literally printed in books. So you can find my email address, email me, and I will help as many people as I can, and I will introduce you to other people who will help you, because I want there to be more speakers and more voices on all the stages of the world. Okay? So think about it. Do it.
Thank you, Kate. Okay, news in the C++ community. Two conferences, two new one-day conferences coming up next month on the same day, June 15th. Still time to go. CPPP in Paris will feature an incredible keynote speaker, Kate Gregory. And the Italian C++ conference in Milan will also be on June 15th. Also, CPPCon is, they're no longer accepting proposals for papers, but they are open for registration. That'll be in September. The call for volunteers is still open and will be open until June 25th. So if you volunteer there, I believe you get your ticket to CPPCon covered. And you can also apply for volunteer grants where they will help pay for your lodging and your airfare. Okay, the next meeting of the C++ committee, the ISO committee, will be in Cologne, Germany. That'll be mid-July. C++20 has been feature frozen, but they are still haggling on the details. Do you guys know if the paper list has been finalized yet? I don't think so. So you can definitely, I don't want to say definitely, I believe that you can still submit papers to get included in the C++ standard, just not brand new features, tweaks, improvements. So more on that later. Okay, so I would like to introduce our speaker tonight, Damian Vicino. Hope I said it right, close enough. Damian has a PhD in computer science with a focus on simulation theory and uncertainty. His over 1 decade of open source experience related to Boost, BSD, and simulation. He is the lead on the Cadmium simulator development project. Currently, he works on Alexa at Amazon, and he's here to tell us about simulation in C++.
Hi. Okay. I will talk a little about what kind of simulation we do. I will spend a few minutes trying to explain the problem. And then I will talk a little about how it was solved in the past and how we are solving it differently and a few things that might be reused in different projects. Oops. So this is super important thing. Whatever I say, not my employer now, in the past, on the future, is related to it. It's just my own opinion and what it says. Okay, so simulation theory. What is simulation theory? Is a lot of math about how to write models and how to generate dynamic behavior from them. So there is 4 big groups of simulation. Pretty much every formalism, there is hundreds falling one of these 4s. One is things that are continuous, like most models from physics. Things that are continuous but sample, so they have discrete time, but it could be in any place, the values. Things that are the opposite is like everything is discrete, like you have sample time, but also have discrete values, and things that has discrete values, but continuous time. That one is discrete event simulation. You have events that could happen in any point of a continuous timeline, and those events are a discrete set. So what you can simulate with discrete event simulation is synchronous communication, signaling systems, microcontrollers, weather. Mostly anything human designed is discrete event simulation, is a discrete system by itself, but there is some theory behind that says that any other formalism can be adapted to be simulated by discrete event simulation. Okay, so from those discrete event simulation formalisms, there is a family of them that is based in what is called discrete event system specification, which is a formalism from the 70s. It's still popular. And it has this property that is universal about depths, discrete event simulation. So if you can simulate it with an automata, you can simulate it with depths. If you can simulate it with a continuous thing, you can use depths. If anything can be transformed into a depths model. And the way a depths model works is it has atomic components, which are components with behavior, and coupled components which are combining behaviors into a structured model. It looks like a tree. And one of the properties it has is that it has something called closure under coupling. That means that if you make a few atomic models and you connect them somehow, there is an equivalent atomic model for that. In theory. In the practice, it's hard to find, but So the other cool thing it has is like it's well structured the way the simulation is separated from the modeling. So you have a model and you have a simulator that is generic enough to run every model on the specification. So you keep the concerns separated. And the simulator is split in two things. One is called simulator, that simulates atomic models. The other one is called coordinator, simulates coupled models. So an atomic model in depth looks like this. It has an input, x, which is sets of things. Oh, we had sound now. Oh. And then, lower. And then we have the outputs, sets, all the valid outputs, and the states. States is the discrete things you can have as values. And then we have four different functions. One that is used when nothing happens for enough time, which is called an internal transition. It's like nothing happens, so an internal event is generated and processed, and it changes the state. The other thing is
Attention, please. Smart sensor security. The fire alarm condition has been cleared. Normal elevator service will
okay, so then there is external transitions without transitions that happen because an external event is injected in one of the inputs at any time. And then there is confluence, is called the other one is about what happens if you simultaneously have an internal and external event, how you resolve that case. Output function is a function that, based on the current state, before running an internal transition, it will output a value in the output ports. And TA is how long it will take for an internal transition to happen using current state. And all that can usually be seen something like this. It's a box with ports and something happens inside. And I'm not going to go into all the details of what happens inside because it's not really interesting about C++, but there is a formal description of that. And a couple model is also a tuple that has an input, an output, a bunch of models inside that could be coupled or atomic, and connections between input port of one to output port of others. The opposite. And the connections are called external input coupling if they go from the external ports to the internal ports, input ports. External output coupling if they go from the internal to the external output ports. And internal coupling if they go between models inside the model. So how was this solved in the 80s, 90s? Using object-oriented programming. They put classes called atomic, classes called couple, and they tried to glue everything as a hierarchy. And what happens is like atomic and couple models become subclasses, so they all have the same kind of ports, the same kind of messages, the same kind of everything. So the way most simulators solve it is like ports started to be a map of strings to values, and that, aside from the complexity, only exploits when you use it. It's like it fails when the simulation is using the wrong port. So you could be running a simulation for days, and it fails. And it's because you assigned the wrong port. So it's not good experience. Then the other thing is like many models couldn't find a way to keep all these functions separated. So what they did, the simulators started mashing up things, so all these functions become only 4. And having those 4 functions doesn't really match with the original model, so for the research scientist that is doing the model, matching it into the implementation is not clear. So it's super hard to find out what is wrong when you get the wrong results. And one of the simulators that did this is the one I'm replacing with Cadmium now. It's called CDPP. It was there for over 20 years now. It has a lot of tooling, and it has hundreds of models already implemented, has a big library, so people keep using it, but it's super hard to find out when something goes wrong. So in one of these, in C++, a model usually looks like this. It's, a receiver comes from an atomic, and every function returns a model, which is an integer, and it receives messages, external, internal messages, which are integers, and it has a string name function that tells you the name of the model, and then internally it uses a map that will map the model and the ports to the messages, and it will pass vectors with things inside maps from one model to the other. So one of the functions looks like this. Is you need to check if the message you're getting is in the right port. That in is an enum, so it's another integer. And then you get the value from the message, which is a single structure for all the messages in the system. And hold in is the replacement of the time advance function. What it does, it says, don't point to this model for this period of time because I'm not supposed to be called. And below is all the three things that this code is doing at the same time. So in the original model, you have three different very clear things, like the state, the time advance, and the function that executes the external event, but in the other one, it's hard to find this match between things. So 10 years later, there was a new generation of models. The way they did is they created sim-level models. They said an atomic model is not in the hierarchy of atomic, it's actually in the hierarchy of simulator, and the couple models are in the hierarchy of coordinators. So internally, you define pretty much everything protected, and what you inherit in is knowing how to call it and make it look the same outside. So for each of these models, it will add functions that simulate internally inside the object. It's way faster, that's good. It keeps passing things in a single type, which is int in most of the cases, and it keeps using map of a string to figure out the ports and stuff like that. So the most common one is ADEPS, and it looks like this. It has internal, external, and confluence functions, output functions, a garbage collector, and everything goes into a file. So for atomic models, it doesn't look that odd, but for couple models, it looks like this. You create a couple model, and you start adding things like it was a container, and each of them will have to be linked with pointers. So everything inside here is a pointer, a raw pointer. And if you just pass the wrong pointer here, it will notice whenever you use it. So the focus on the way we try to approach it is, okay, this is a recap of what's wrong. It's hard to map what you want to do with what you're doing. It's super hard to find out when something fails in advance. So usually it doesn't fail on compile. It usually doesn't fail in initialization. It fails when you use the wrong port. And since all messages are int, it might not fail, which is even worse. So you know that you have these people that is crossing the traffic light, and at some point you say, okay, the traffic light changes from Martian to human, but since it's 1 and 2, you don't know, and it's fine. So, and all of them use a lot of threads, and it's super hard to find out if you're executing the right thing. So, what else is wrong? They also have too many dependencies, all the dependencies, and again, the validation. So we don't want to solve every problem, so we try to focus in two scenarios, two kind of use cases. One of them was simulation-driven design. So in simulation-driven design, the idea is that you start with a model with many sub-models, and you start replacing what you do out. You take part of the model out, and you replace with real things until you get the whole thing working. And I have a video example, but I think I didn't connect to internet, so it's a robot. It's a robot that we have running our simulator inside, and it follows a track, but actually the track is simulated inside, so it might go some other place because the camera is not real. But later we put a camera on it. So. And the other one we wanted to do is forecasting. We wanted to run something that we have one model, we build it, we build a simulator for it, and we will use it for a year. We are not going to iterate every 10 minutes, not focus on development, focus on use. So we made a list of requirements. We wanted it to map theoretical model to the model we see in the code. We wanted to fail early, make economic in reuse, be extensible to other formalisms. There is a few of them that are very similar, and they provide some small changes will make it work. No overhead on runtime when doing coupling. We don't want things like the store adding to the map, and in the middle of the simulation, someone can add one more model in the middle. Easy to trace, support multiple platforms, including embed because we were working with robots, a predictable memory footprint because we wanted to put it inside very, very cheap things. So at least we wanted to know that we can run something that will not hang out in one day. Okay, so what we use for this is we make it super strongly typed. We use type for everything. We decided that there is no hierarchy, that an atomic model is just a model, a concept, and a couple model is also a concept, and they are fine with that. We wanted to fail on compile time every time that you connect two things that shouldn't be connected. We make a lot of template metaprogramming policies for doing that. We wanted easy to trace and cross-platform and low dependencies. For cross-platform, what we did is we just follow the standard. For low dependencies, we only use Boost, and for testing. Without testing, not even Boost. So this is a model. This is the starting point we had. This is a real model written in the formalism. So we have the state, we have the different ports. Each of them has a definition of what we are moving between the ports. So we know that the first port is sending packets. This model is for alternate bit protocol implementation between two machines. So one sends a packet, the other one sends an acknowledge and reads the data and move it to a different machine. The state is, it could be waiting or it could be doing something. And 0 and 1 are the alternate bit. It's 0, 1, 0, 1 when you reply. Once you send a message, the internal transition will say that you wait for something to happen. And the external transition, what it does is it will read the packet and save it into a state. And the confluence transition, what it does actually is it will first run the internal, then the external. Output function will output the ASIC acknowledged for the message received. And the time advance is if I have something to return, I do it immediately. If I don't have anything to return, I wait. So we wanted to keep it as simple as this when we do it in C++ and easily to match. So this is how things match. We defined something that is called a struct port that has two pieces. A port has a kind of port in out, and it has a type of message that the port will handle. And the type of message is a template, so anything can be passed as an input or as an output. And we did the same for the output. We have two ports. So a set of ports in this simulator is a port for a kind of ACK packet, a port for data, and the whole thing is two ports in a tuple. We did the same with the state. We defined the state as some struct that you can pass as a template parameter. And here is where the things start to complicate. An internal transition is fine because it doesn't return anything. But an external transition has to deal with time and with the external event coming from X. So the way we deal with that is that we have a constpress that will transform the input ports into a bag of messages that could come from those input ports. And we use that as the type for the signature of the method. And we use time, which is a parameter of the whole simulation. And using get and using the types of the ports, we access by type to get which message comes from which port. So we want, in this case, in get phase state, is getting from the state the phase. The state has two parts. So in the other, on the bottom is we get the alt bit. Part of it is a tuple of things, and it matches exactly what's in the specification. So Confluence does the same, and output has to return the kind of output ports messages, and it will read the things using the get from the tuple using type at get. So this was constrained us to go to C++ 14 at the time. So, and time advance returns a time, and internally doesn't have anything interesting. So the final definition of the whole model is just a class that receives time as parameter, and inside that we define all these little pieces. And it looks pretty much the same as you have in the paper originally. But it's typed, it's well typed. It has a lot of types around the ports and the messages and all these things. And then for the couple model, we have a couple model like this. This is a model of a clock. A clock has 3 needles, hour, minute, and seconds. And each of them tick. And they are connected to the output. One ticks every hour, every minute, every second. The last one, the EOC, is the way it is connected. So from the output to a clock with H, it will output to the H exit, the other one goes to M, and the other one goes to S. So how we do it inside the simulator is we define the input ports as a tuple, empty because there is no input ports. And we define 3 output ports that tick. And we put them all together into a tuple. And then the submodels, we just have a constpress that makes tuple of models. In this one, we don't use tuple because a model has a non-instantiated template parameter for the time. So it cannot be passed as a type yet. It's a template. The external input coupling is empty, and the external output coupling is just telling that which model and which port of that model is assigned to which port in the current model, in the top-level model. the internal coupling is empty, and the whole coupling, the whole model of everything, the couple model is just defining something called couple model that has a parameter, all these things, input port, output port, set models, and so the idea is using all this type information to tell the intentions of the modeler. And what we do with all this information is we validate. Once you pass the whole model into the engine that will process the model, first thing it does, it will put a lot of asserts, static asserts. So it checks, for example, that if you connect an input port and an output port, the message inside those ports is the same type. And it checks that the type you're using for returning from an external transition function, it will be the one that the output port is expecting, and the internal, and it does the same for everything. And this gives us the chance that we are arbitrarily typed. Everything can be as specific as you want, and you can use a structure for internal representation and for passing messages around. We also validate that all the functions are defined, because since it's not a hierarchy, there is no validation for that. And then we have a lot of policies for logging, because internally we have logging, and the way we handle it is like we use the sync format filter pattern. But we implemented it using template metaprogramming to just remove it when we don't need it. So this is how a port looks like internally. It's something of the enum class port kind in out, and internally it just gets the message. And we have a helper function that gives you the way to just read the messages from that specific port. And the in port is using the kind in, the output port is using the kind out. So what we found is that at compile time, it might not work if your model is too large. So we were using all this for small things like 20, 30, 40 models connected between, and someone said, I want to study cancer, and I have 8,000 of models of molecules to connect between them. It didn't compile. So we implemented an alternative thing for the couple models. So we have now a couple model that is actually an object, and it gets pointers to all these things. And it still validates most of the things we validate, but some of them exploit in initialization time. So it's not exploiting on runtime. It's just at the moment you start the application, it will try to validate everything. For long term, we expect to fix our issues. We found what's the reason. The reason is like, every time we check the whole tree of models, we are checking the whole tree of models every time. So when you start on the atomic, it's checking the atomic, and when you couple the two of them, it's checking the couple and the two atomics, and when you couple again, it's checking the couple, and the couple you check it, and the atomics, and it's kind of quadratic, I think, in the compile time. We also plan to move, as soon as C++20 is available for embedded, to move to concepts, real concepts, and hopefully that will solve the problem. There was a bunch of side projects that come up from this. There is a benchmark tool for this kind of simulator that was around for about 20 years also, and we adapted it to make it work with our simulation. A diagrammer that outputs a graph showing all the models, a parallel version of the simulator that is on progress now, and 2 projects for Boost that are in proposal stage, been working on the whole summer of code. So for the future, we want to make it C++20, real time. We want to explore the include OS. I don't know if anyone used that yet, but it looks like an amazing project. It just, you include OS, and you get a binary for running in a virtual machine. You get an OS. So we want to give it a try. We want to document better because it's poor. And the things we learned is that there is no time to fail earlier than compile time. That guided us through the whole process all the time. It's like, you can check on runtime, or you can check an initialization, but compile time is also possible in C++. It's something that in other languages is not available and is super powerful. Working in a library is like, we really learned a lot from doing this example of, okay, how I want this code to look for the user. And then we do all the things to make it happen, like the way I showed, like this is the model, we wanted to look it similar, but in C++ it's very different to the approach that was taken before, that was like, this is the formalism they are giving us, I have object-oriented programming, and how do I squash these two things together? We learned that compile time testing is not what we expected, because what happened is like, we started testing all our static asserts, making things fail in compile time. So we use CMake, and CMake will try to compile all these things, and it will check like, okay, they fail, they are good. That's how we test that our assert works. But once we upgraded the compiler, and everything was failing, and it was good. So we also need positive cases all the time for every test. And giving the possibility, users will provide the types and will make things valuable information that you can use at least in simulation that was not available before. I wanted to show a little of the code of the simulator, but I noticed that it was a huge thing with a lot of espionage all around, and nobody really wanted to look at that. But everything is open source. It's available in GitHub, and you can ping anyone in the team. We are all there. We always reply. And is questions?
I've been looking for something the past few weeks which will just render ports and graphs with ports. The only thing I found was GraphML, but it's not supported very well. Do you know anything that will do renderings of?
I don't really know what we are using in depth diagrammer, because I never touched that code. But GraphML sounds like very popular now, so I'm not sure what. I usually live in the world of backend. I don't touch pixels much, so.
So you mentioned that one of the side projects was kind of a benchmark for the different event simulators. So where does your solution stand performance-wise compared to
Okay,
other
so we had the group I worked with is, they were originally doing CD++, the first one. That was about 600 slower than the second one I showed, which is from another team. We make an intermediate implementation of this, and we compared it 3 years ago, and we were, worst case, equal to them, sometimes even 1,000 times faster. And this one, we're still working on getting a real measure, so we don't have it yet, but we expect it to be even better. Mostly what we're doing is we move in stuff that is solved at runtime into compile time, so we try to get all the way you construct the you allocate memory. For example, when you have pointers, you start allocating memory, allocating memory, allocating memory. This one is in the binary. We have, I think, one pointer in the whole code base. So it's like you pick up the binary, you put it in memory, and you start executing. And that gives you a lot of runtime freedom. But something that is very particular of this problem is like, you know how it will look like in execution time. Because once the model is there, the only thing you do is you put some input and you wait for an output. And you sit there maybe a week for that. But it's a very particular software. It has no interaction.
I actually have one question. First of all, I agree with you that the way you've designed Cadmium, it's a more modern and more elegant way to approach simulation. That said, it appears that the programming paradigm is going to be basically turned inside out. What reaction have you had from the simulation community?
Okay, from simulation community is very funny, but what we see in research conferences is like pretty much every research group that is big research group in simulation has its own simulator. So the only contact they have between each other is like, let's compare. So for ours, what we notice is like, we are using it as a teaching tool in 3 universities, and people is happier than before, but because they were using C++. So, but it's not like still on that level of adoption or anything. It's like, we call it 0.3. But we didn't found a lot of adoption yet. Like, we don't have a user base enough to tell something about it. It's like, but it's something super common in simulation research, because we are moving in the area of research, not from the university, not from. But we saw that we made some impact in triggering the discussion for real implementation in Boost, because all simulators, everything that they use for time is float. Float is a way to fail doing discrete event simulation. It makes you sometimes flip the order of the events. Yeah. So it triggered a lot of discussion about how to use it. The other thing is like, in the universities we interact the most, they don't use C++ at all. So they do it in Java, they do it in Python. There is one in Smalltalk. I think the cutest one is Smalltalk. The other ones are like, doesn't match the problem that easy.
Hey, so I have 2 questions. The first one is it possible in your simulator to snapshot the state of the simulator at a point in time and either kind of like resume there?
There is an intention for that. We are working on that, and that's why it's a minor detail in the slide, but the state is a public variable with a fixed type. The type needs to be treated as a trait. It's mandatory. We are checking that the trait is always there and that the state is accessible from outside. So our plan is to do recollection of all the states variables from the whole hierarchy and save it and load it. We don't have it yet.
Okay.
It's in progress.
I see. And I just wanted to ask, 'cause I was a bit
just one thing about that. You can pause it and continue now. What we don't have is the dump and load. So if you do a simulation, you can tell the simulation run for 50 minutes, simulation time, check something, and continue for another 50 minutes or stuff like that. That's available. What's not available is dumping and continue.
Okay. I see. And so the other question is, you had a bunch of categories of simulations, and is the one that you're doing continuous time and continuous value simulation?
No, ours is continuous time with discrete set of states or events. An event is a discrete set of changes. So when you visualize it, it's like a step function.
Yeah.
So you could have any time, jump, anytime, jump. That's the time of the event.
Oh, okay. Okay. Yeah, I was just wondering because one of the problems in the chip design world is that they have these really old simulator tools that they call SPICE simulations, which are horrible and very slow. And I was just wondering if
What
you guys are working on
this
stuff
is a
related to
good
that.
match for processors, for networking, for that kind of stuff is a good match. We had in the previous simulator in CPP, we have someone modeled the Spark processor, the Open Spark processor, and they also modeled an operating system working over it. So you can run small programs in binary. If you got the ELF, you can run it and you can see the prefetch and fetch and all the pieces inside it. It will take forever to run a small program, but but you can go very detailed about what's going on inside. It's doable, but one of the things about this general purpose simulator is like they are general purpose, they don't have tools. So you don't have something that you put there and it's a router. It's like you have something that sends and receives events and you need to model. We started working in a small library with common things, but we have very few models. The other one has a few hundred and we plan to migrate. But the way we migrate is like, it's a final work for some of these professors. So a student has to do it. So they have the option to do it. They need to choose.
Okay, let's thank our speaker one more time. I'd like to present Damian with some traditional CPPTO chocolates.
Thank you.
And thanks again. That was a fantastic and fascinating talk.
Thank you.
So a couple things at the end. Our next meeting is going to be on June 25th, and it's going to feature Diego Rodriguez Lozada. This is actually the co-founder of the Conan Package Manager product, and he's the current lead of that product. He's going to be in Toronto for a while from Spain, and he's going to come and talk to us. If you're interested in speaking at a future CPPTO event, please contact us. Always looking. I think it looks like we're going to take the summer off. We'll be back in spades with bells on in September. So that means there's 10 months in a year. Also, if you think you might be interested, as Kate said, drop us a line. Jump onto the Include C++ Discord. Tell people you're thinking about talking. Is it an interesting idea? How can you develop it? You will get lots of help. And we're also looking for sponsors. We're always looking for sponsors. These events don't run themselves. So if you think that you or your company would like to step forward and run some of these events or host some of these events, come talk to me. That's fantastic. I think we can make a good case that we're putting your name in front of some of the best developers in the world. Okay, so speaking of sponsors, our sponsor tonight has a few jobs available. So they get the prerogative of showing their hands first. So why don't you guys raise your hands? Okay, so there are some jobs available. These guys know about them. I can personally vouch that these are great jobs. One of them used to be mine. Okay, so how about anybody else? Does anybody else have a job that they are looking to fill? People they're trying to hire? Okay. Okay. Or knows of somebody who is. Raise them high, raise them high. Okay, now, who are the folks who are looking for a job? Okay. Guys,